Okay, welcome. This is Chapter 7, Part 2. This is the last of the chapter. We're going to look at impulse, elastic collisions, and inelastic collisions. Okay, first we'll start out with just impulse. What is it? An impulse causes a change in an object's momentum. So if an object has a momentum, or even if it doesn't, it's the impulse that causes it. Well, we know that through Newton's second law that forces cause the change in momentum. So sure enough, the formula for the for impulse comes from the force equals a change in momentum over time. So this is Newton's second law. We then rewrite it so that it's force times the change of time. This is the time that the force is applied. We'll change the momentum, and then we give this thing on the left a goofy symbol, J, and J is the impulse, and it's equal to the force times the change in time, which also equals a change in momentum. Impulse doesn't have any particular unit. We'll use Newton times seconds if we're ever talking about the value of the impulse. So what we can do with this is we can look at the formula for impulse and analyze each part. F is the average force that's exerted over the time. So even if the forces change during that time, we still just want the average force. Delta T is the time that the force is applied, and F delta T is the impulse that we're looking at. Okay, and delta P of course is the change in momentum, and that's what we've been talking about up to this point. The impulse can cause the change in momentum. So a change in momentum is either the difference in the final momentum to the initial momentum. So we can subtract momenta in order to get the change in momenta. That's one way. A change in momentum can also be mass times the change in velocity. So if you're given the velocities and the mass of the object, then you can find the change in momentum. And this is basically broken down to m times v, final velocity times initial velocity. And that, of course, is equal to impulse. So there's a lot of different ways to look at it. Very seldom do we actually, calculate what the impulse is. But what we do calculate are the forces involved during the change in momentum. So let's take a look at the first example here. I can serve a 60-gram tennis ball at 65 meters per second, not miles an hour, 65 meters per second. The time of the hit is 30 milliseconds. With what force do I hit it? So of course I'm going to use this impulse formula, which says that F delta T is equal to change in momentum. I'm going to then rewrite the change in momentum as mass times a change in velocity, because I have the final velocity here, and we're assuming that I throw the ball straight up, so it doesn't have an initial sideways velocity, and that's when I hit it. I then do the algebra first. There's was with the right side, and I divide by the time. I drop the delta because there's no initial and final time. It's just the change in time. Okay, with that you can put in the numbers. You can put in the mass. Be sure you're in kilograms. Put the change of velocity in, and then you'll need to switch the milliseconds into seconds. A milli is times 10 to the negative 3. So it may seem a little cheating, but all I do is take that milli, which is 10 to the negative 3, and replace it with times 10 to the negative 3. So this is not in scientific notation, but it works just fine in your calculator. And there's my kilogram mass. I calculated. Go ahead and calculate that and pause if you need to. So the result is 130 newtons. So it makes a little bit of sense. The force to get that 60 gram ball going to 65 meters per second is 130 newtons. What if the ball was coming at me? So now this is not during the serve, but the ball is coming at me at 50 meters per second. Do I have to hit it harder in order to hit it back at 65 meters per second? Well, we can just basically look at this formula here, right? Because we're basically doing the same thing. We're looking for the force. So now we put this in, but look at this. The final velocity will still be 65 meters per second, but because it's coming at me, then I'm going to subtract a negative 50. So sure enough, I subtract negative, that means I'm going to add those two velocities together. And in fact, I have to hit it 230 newtons. So I do have to hit it harder to change its direction. So you have to think about, if it's coming at me, I have to stop it and then change its direction and then get it going 65 meters per second. So it takes, quite a bit. Not quite double, but quite a bit. Okay, so now we're going to look at conservation of energy during collisions. The first type of collision we look at is what's called a perfectly elastic collision. Now, the word perfectly doesn't always get into the story, but if it says it's an elastic collision, then we assume it's perfectly elastic collision. During a perfectly elastic collision, kinetic energy is conserved. We also know that momentum is conserved, but this is just doing a perfect elastic collision. That means all the energy is transferred from one type of energy to the other. And so we basically look at, let's say we had two objects, both with kinetic energy, that exhibit a perfectly elastic collision. So then it would take the initial kinetic energy of the first object plus the initial kinetic energy of the second object, and that would equal the final kinetic energy of one object plus the final energy of the other object. That's how you would show that the energy is conserved during that. During inelastic collisions, kinetic energy is not conserved. So we'll look at some examples of that. But basically what happens is you have this happening, but you also have other forms of energy like heat energy, sound energy, and this special kind of energy I just call smush, which just basically puts the atoms closer together. Think of it like compacting a snowball so they're closer together. It takes energy to do that. You could call it pressure or something like that, but it's much more descriptive if I use the word smush. During elastic collisions, it's conserved, not conserved energy for the inelastic collisions. But keep in mind that momentum is conserved during any collision. We learned that when we in the first part of this chapter. So we're going to take a look at some examples of that. So elastic collisions in one dimension. So energy and momentum are conserved, like particles that collide in line retain their relative velocity. So if we had this green object moving with a small velocity and this red object moving opposite towards the green one, and they collide, and the collision is perfectly elastic, then they actually will exchange velocities. That is, if the particles are exactly the same. We can take a look at how this is called relative velocity and how that works. We treat momenta as vectors, so that are conserved. So these are all in line with each other, so it's easy to see that. We will look at an example where we have vectors that are not in line with each other, and those are a little bit more tricky. Okay, so we're going to look at the relative velocities in elastic collisions. we know that kinetic energy and potential energy are conserved. If we substitute the formulas for each of those and rearrange it, then we have this. This has to do with the momentum being conserved. This is of object 1 and object, or mass 1 and mass 2. And this has to do with the kinetic energy being conserved. The 1/2s are gone because they cancel on both sides. And if the masses are equal, we have the relative velocities staying the same. So that means the difference between the velocities at the beginning will be the same as the difference between the velocities at the end. If you want to peek at what the math looks like on this, keep in mind you'll never have to do this for me, but this is what the math looks like for it. And this is just using the conservation of energy and the conservation of momentum, and what you end up is a system of equations, and it's somewhat complicated on that. So that's probably enough to looking at that. So let's look at an example. We have a red bowling ball that has a mass of 7 kilograms rolling down a lane and slowly, 1.5 meters per second. And I have this blue bowling ball coming from behind it that's also 7 kilograms. But now it's rolling at 5 meters per second. What are their respective speeds after they collide if they don't change directions? They don't go off sideways. They just keep on going down the lane. So the first thing we're going to look at is the conservation of momentum. So that says that the initial momentum of the system is equal to the final momentum. The momentum before is just going to be the sum total, and the momentum afterwards is also going to be the sum of them, because they're not colliding, they're not smashing together, they're bouncing off each other, assuming that it's elastic collision. At the beginning, now we're coming off of the initial momentum is the mass times the velocity of the red ball plus the mass times the velocity of the blue ball. And that's going to equal the mass times the velocity prime of the red and the mass times the velocity prime of the blue. Okay, so that's all coming off of the conservation of momentum line. Because this is 7 kilograms and that's 7 kilograms, we can actually cancel out all the masses, and then we end up with the velocity of the red plus the velocity of the blue is equal to the velocity prime of the red plus the velocity prime of the blue. And that way you can see from the last slide that if I bring the red over to the red and the blue over to the blue, then the relative velocity will stay the same between the two. But let's go ahead and put the numbers in. So we have 1.5 from meters per second for the red one and 5 for the blue one. And then we don't know either one of these. So what we're going to end up doing is looking at the conservation of momentum and the conservation of energy, and then putting it all together. So I just rearranged this. I add the 1.5 and 5 together, so 6.5. So I have those two. I then am going to solve for one of those, and I solve for the velocity prime of the red. It's arbitrary which one you solve for, as you'll see in a second. Now I'm going to address, because it's a elastic collision, now I'm going to look at the conservation of energy. So the initial energy is equal to the final energy. And of course, just like the momentum, the kinetic energy is equal to the sum of the two respective energies. I then put in formulas for that, and this becomes long because the initial is 1/2 mass of the red, velocity of the red squared, plus mass of the blue, velocity of the blue squared, and the final is 1/2 mass of the red, velocity prime squared, and 1/2 mass of the blue, velocity of the blue squared. It's harder to say than it is to do. Well, because every term has a 1/2, and because the two masses are equal, we can take out the 1/2 m from every term, and it cleans it up pretty well. So this says velocity r squared plus velocity of the blue squared is equal to the velocity prime squared and velocity of the blue squared. Okay, now I'm going to go ahead and put the numbers in just like I did over in the momentum side. So, but now I have 1.5 squared plus 5 squared is equal to this sum of the squares of the velocities. And so now I square and add these together, and it comes out to 27.525. So now I have this equation, and I have this equation, and I'm going to combine the two together. Just like in algebra, when you had two equations with two unknowns, you combine it together to solve it. So I'm going to take this VR prime, and I'm going to replace that in this equation over here. So the 6.5 minus VB comes in here, right? And now my next algebra step is I have to clear this parentheses. So I have to square this binomial. So be careful on that, because it's just like, it's not just that squared minus that squared. We have to do the FOIL method. So we have 27.25 comes, and now this FOILed is 6.5 squared, and then that times 2, and then that squared. And because that's negative, that positive, and that was negative. All right, and then so I just kept the parentheses in there to show you where that trinomial came from. I then collect like terms because I have a VB prime squared and a VB prime squared, so I have two of those. So I'm going to put those together. I'm going to bring the 27.25 over so that I now have this trinomial. So this is 2 VB squares. The minus 13 VB stays because I'm bringing this over. I subtract 27.25 from 42.25, and I get 13 VB. Okay, now we solve this equation. You can go ahead and pause the video and solve that equation and see what you get. Well, I got the velocity of the blue afterwards is 1.5, and the velocity of the red afterwards is 5.5 meters per second. I put this equation in a graphing calculator and found the roots. That's how it came out to 1.5 and 5. Right? And to me, I've told you before that the graphic calculator, to me, is the easiest way to get the roots of those. So, as you can see, the red now is going 5 when it was going 1.5, and the blue is going 1.5 when it was going 5. So, and logically, that makes sense. If this fast ball comes up behind it, it's going to hit it and slow down, and then the other ball will pick up the speed that the other one lost. Now, if the masses are not equal, then the algebra gets a little trickier. But you can still do this. It's just a little bit more difficult. You'd have to you couldn't cancel all the masses out there. You'd have to get one mass in terms of the other. I won't have you do that. The hardest one would be something like this. Okay, now we're going to focus in on inelastic collisions. These are collisions when two objects stick together and become one. And as I told you a few minutes ago, kinetic energy is not conserved. So we can't use the conservation of energy in order to find anything. But remember, we still can use the momentum is conserved. Energy is lost during the collision. Remember, it's lost due to heat exchange, sound, and smoosh. And so we end up with the energy looking like this. Excuse me. The initial kinetic energy is equal to the final kinetic energy plus this lost energy. And once again, the momentum is conserved. So we can find out a lot using the momentum and all. Okay, remember the cars we studied when we were studying, we did the first part of this. We have one train, the B train, is 10,000 kilograms, sits on the track. It's at rest. And the A train, which is coming from the other side, it's 15,000 kilograms, and it's moving at 24 meters per second. Now, we calculated that they move away together at 14.4 meters per second. Right? That we use the conservation of momentum to do that. Well, now the question is how much energy was lost. So we're going to use this 14.4 that we calculated earlier. So we take a look at the Initial kinetic energy is equal to the final kinetic energy plus this lost energy, and we're going to solve for that lost. So we put the formulas in for energy. We have the kinetic energy of A and the kinetic energy of B is equal to the kinetic energy of the combined train AB, and then we have this lost energy. So this is just basically plugging numbers in. I went ahead and left. I have to leave the 1/2s in this time because there's no 1/2 in that term. So a 1/2 15,000 times 24 squared plus 0, because this is a 0 velocity. I don't even need to put this in, but I did to show you where it went. Plus 1/2 of the combined mass times 14.4 is the velocity that they go off, and we square that. So we do our do some math now. This comes out to I multiplied 1/2 15,000 times 24 squared. That's 44,320,000. I then added these together, multiplied all that out, and then moved it over, so I subtracted it. And so it's 2,592,000 joules. And you can pause and calculate that if you like. Energy lost is 1,728,000 joules, or 1.728 megajoules. So quite a bit of energy is lost there. We keep in mind that the momentum was conserved. And I know maybe that bothers you, that how could one be conserved and the other one not? But that's just the way physics works. Okay, here's our next example. It's called the ballistic pendulum. Ballistic means that it has to do with guns and things that shoot bullets. So if a bullet has a mass of 50 grams and it strikes a block that is 2 kilograms, that is at rest, and it swings up, the two of them swing up on this pendulum so that it's 1.4 meters higher, and then it stops, how fast is the bullet going? So we can use the conservation of energy. We can only use the conservation of energy after the collision. So we can look at, we're going to look at this backwards. We're going to analyze this B picture first, where we have the combined masses and it has this initial velocity, and then it moves up. But we'll be able to calculate what initial velocity it was, because we're going to use gravitational conservation of energy, where the kinetic energy of this before, like, it had velocity and masses, and then it moves it up the gravitational field height of h. So we put in 1/2 mass of the bullet and block, velocity bullet and block squared, so that's kinetic energy, is equal to the potential energy, the change of potential energy, 1/2, or not 1/2, but mass times the sum of the masses, g times h. Okay, so VB, this is the velocity of the bullet and block after the collision. So once we're going to calculate that and use it, and then look at the conservation of momentum of the collision. So this conservation of energy works because there's no collision happening from when it's, as soon as it hits, until it comes up. So we put in the numbers, 1/2 mass, and that's the total mass, velocity squared, equals mass, g 9.8. I crossed out the masses because you don't need to have them in there. You could have canceled them up there, but I'm showing you there. If you like having the mass in there, you can go ahead and calculate it. Okay, so that's a pretty simple calculation. Multiply 9.8 and 1.4 together, divide by 2, or 1/2, or multiply by 2, and then square root. So the initial velocity of this event was 5.24 meters per second. That happens to be the final velocity after the collision. So we're going to use that. We have an inelastic collision happening in the A picture, so this means the momentum is conserved during the collision. We can't use the energy. We can only use the momentum. But that's generally easier because the formulas are more simple. So the initial momentum is equal to the final momentum. The initial momentum comes from the momentum of the bullet and the momentum of the block, and the final comes from the combined masses and the velocity that we just found. So formula looks like this. There's the bullet momentum, there's the block momentum, and this is the bullet block momentum. Put in the numbers. Reminder, of course, for the grams, we have to make sure we're in kilograms. This is the velocity we're trying to find of the bullet. We have no momentum of the block because it's hanging still at the beginning, and then there's the combined and the velocity we just found. The math is pretty simple on that, much easier than the last one. You could do that if you like. So the velocity of the bullet comes out to 215 meters per second. And this is actually how they can calculate. I'm sure they probably have more complicated ways or electronic ways of finding the velocity of bullets, but this is a way they used to use these ballistic pendulums. Okay, so let's take a look at one last example. We have a Toyota with mass of 1,000 kilograms going north at 20 meters per second, and it collides with the Cadillac that's going east at 9 meters per second. The bumpers lock together and they slide together before stopping with the coefficient of friction, sliding friction of 0.4. How far did they slide and in which direction? So we're going to analyze this. We're going to look at the conservation of momentum during the collision, and then we're going to use the conservation of the work energy conservation after the collision. So before the collision, we have momentum of both objects, and then we're going to find, and then after they're combined together, we have a momentum of the combined vehicle. So but you have to be careful because this one's going north and this one's going east. So now I have to look at these as vectors. So the black one represents the Toyota that's going north, and the red one is the Cadillac going east. I didn't draw these to scale, so just give us a picture. And so the green one would represent the final momentum. And so we use Pythagorean theorem in order to find this momentum of the Toyota Cadillac. And so the Pythagorean theorem just looks complicated, but it's really not. It's the square root of momentum of the Toyota squared plus the momentum of the Cadillac squared. And that comes out to 28,143 kilogram meters per second. Fair enough? All right. So now that we have the final, we do have the final momentum, now we could calculate what the final velocity is because we're going to put that number in into the momentum formula and then calculate the velocity. So that's pretty simple. We take the momentum we just calculated, 28,143, divided by the total mass because this is the Toyota Cadillac object. We divide that out and we get 8.8 meters per second. So this is the speed at the start of the slide, right? So this could be a picture of the momentum vectors. It could also be a picture of the displacement vectors, if you will, or the velocity vectors. And it could be any one of those because they're all going the same direction. So now we're going to look at the second part. We haven't answered the question yet. We haven't figured out how far, but we're going to use the work and the distance that is in the formula for work. So we use that formula, and so the work done by friction is the normal force times the coefficient, so it's mu mg of this large object, times the distance to get the work, and that equals the change in kinetic energy. So imagine that it has all this kinetic energy when it starts sliding. And so this is what we're calculating here. And we're going to use this velocity we just calculated right there and total mass. So I put the numbers in like you would normally do. I put the coefficient in. I put the mass of the combined object, 9.8 times the d, then that's what I'm looking for. 1/2 of the mass times the 8.8, which I just calculated. And once again, I cross out the 3,200 because I don't need to calculate that because it cancels on both sides. All right, so now you can go ahead and do the math because the next click is just going to show you the answer. If you want to go ahead and calculate it, pause the video. So I took the I took 8.8 squared, took half of that, divided it by 9.8, divided it by 0.4, and I got 35 meters. So it's going to move off at 35 meters from the collision. The next question, though, is in which direction does it go? So I'm going to now look at this as a position vector diagram. And so the angle would be right here. And I'm going to just do it in reference to the north line, which is the way the Toyota is going. I guess it's arbitrary what reference angle you use, but it seems like a convenient one. So I know what all of these vectors are, but I'm going to use the momentum of each of these because I really don't know what the distances are. I just know that green distance. So I'm going to use the momentum to calculate the angle. So I have the opposite side and the adjacent side, so I'm going to use the inverse tangent in order to do that. So it's the inverse tangent of this is the Cadillac initial momentum, right? 2,200 times 9. And then over the Toyota momentum, 1,000 times 20. And then the math is just calculated work. You could put it in just like that, or you can calculate this first. And then the angle ends up to be 44.7 degrees east of the north. Well, that's a very complicated one, I know. Can get more complicated, but for right now, we'll just leave it like that. So thanks for listening. That's the end of Chapter 7. Get a hold of me in the usual manner if you have any questions. Thanks for listening.